Okay, I'm going to get started with today's class. Let me give a little introduction to what we're going to talk about in today's class. So the last few classes, we've covered rotational equilibrium of rigid bodies. That's the condition when the forces, the sum of the forces acting on the body is zero, the sum of the torques acting on the body is zero. We talked about rotational motion of rigid bodies. That's when the sum of the forces is non-zero and the body will accelerate. In general, the sum of the torques is non-zero and the body will undergo an angular acceleration in general. And to explore those things, the rigid body equilibrium, the rigid body motion, we introduced torques and their relationships to forces. We introduced center of mass and moment of inertia in the description of rigid bodies. So that's been the past few classes. Today's class, I want to move on and look at rigid body motion from a different perspective. And we're going to introduce the concepts or ideas of rotational kinetic energy, angular momentum, the kind of mirrors or analogs of translational kinetic energy and linear momentum that we talked about in the past. And we're going to apply those new ideas of rotational kinetic energy and angular momentum to some old problems that we've already discussed, like the sphere and the cylinder and the ring, rolling down the incline, and some new problems. We're going to explore some new problems with these new tools. So that's the plan, that's the proposal for today's class. Let me just introduce in words the most basic concepts, the most basic ideas that are in today's class, that are the foundation of today's class. So the first one is that the idea of rotational kinetic energy. It's the idea that when something is rotating, it possesses rotational kinetic energy by virtue of its rotational motion. Rotational kinetic energy, we'll find out, is transferred to and from an object by torques. We can think of torques as the agents of transferring rotational kinetic energy. And any rotating rigid body is the owner of rotational kinetic energy. And this new viewpoint perspective will give us a deeper understanding of the rotational motion of rigid bodies through conservation laws that apply to rigid bodies. So that's a big concept in today's class. The other big concept in today's class is angular momentum. Angular momentum is also something that's possessed by a rotating object, a rotating rigid body. It's a characteristic of a rotating object or rotating rigid body. It's transferred to and from the rigid body by the action of torques, and it's owned by those rotating objects. And it likewise offers a sort of a deeper understanding, a fuller understanding of the rotational motion of rigid bodies through conservation laws. So these are really the big topics for today. These are, I just think of them as the rotational counterparts of translational equivalence. So in translational motion, we talked about kinetic energy, and now going to call it translational kinetic energy. And in translational motion, we talked about momentum. I'm now going to call it linear momentum. And rotational kinetic energy, translational kinetic energy are rotational translational counterparts of energy by virtue of movement. And angular momentum and linear momentum are rotational translational counterparts of momentum by virtue of movement. And so what we're doing today should remind us of stuff we've done in the past. When we talked about kinetic energy, linear momentum in the past, it gave us a new, deeper understanding of translational motion. When we talk about rotational kinetic energy and angular momentum today, it will give us a corresponding deeper, fuller understanding of rotational motion. So that's the big picture. Okay, so I want to start by introducing definition of the rotational kinetic energy of a rotating object. And we're going to talk specifically about the work done by torques on a rotating object and draw an analogy with a previous topic, the work done by forces on a moving object. So this slide is really a reminder of something from the past related to translational motion and work done in translational motion. And then I'm going to update the slide to be in the present to represent the work done in rotational motion. Okay, so in translational motion, we might think about a block or a crate or an object. It's on this slide here. Let me get my pen going. Here it is. And it's moving from left to right across the tabletop. And we could imagine pushing the block across the tabletop from left to right, exerting a force on the block across the tabletop from left to right. And when we do that, from an energy perspective, from an energy viewpoint, we think of it as doing work on the block, as transferring energy to the block. And that work that's done on the block, that energy that's transferred on the block, appears as a change in the kinetic energy, a corresponding change in the translational kinetic energy of the block. And so that's the energy perspective. When you exert forces, you transfer energy, and the amount of energy that's transferred by the net force is the changing kinetic energy of the object, of the block, of the crate. We can write an equation that describes all that, and it's here. So this was the key equation. It's called a work-energy relation. And if you look on the left-hand side of this equation, over here, this is the work that's done by the net force. So the F is the force that's acting on the block, and the W here is the work, the energy that's transferred to the block. And then over here on the right-hand side, this is the changing kinetic energy of the block. And that changing kinetic energy of the block is the difference between the final kinetic energy and the initial kinetic energy. And here are the equations for kinetic energies in terms of the mass of the block and the speed of the block. It's 1/2 mv squared. And so that equation, this is, as I say, the work-energy relation. Tells this story of how forces transfer energy, they do work, and that energy changes, increases, decreases the kinetic energy of the moving object. And we can recognize that kinetic energy of the moving object as 1/2 its mass times the square of its speed. So that's a big story on that slide. There's the same story in rotational motion. Let me go to that. Okay, so now instead of thinking about the work done by force or the net force, let's think about the work done by torque or net torque. And to think of that, let's imagine instead of a crate or a block on the desk that we're moving from left to right, we've got a wheel or a ring or a sphere that we're rotating clockwise. When you exert a torque on the rotating rigid body to change the rotational motion of the rotating rigid body, that torque transfers energy to the rigid body. It does work on the rigid body. And that energy that gets transferred to the rotating rigid body, that work that gets done on the rotating rigid body, it appears as a change in the rotational kinetic energy of the rigid body. And so that's the story. It's the same story for translational motion. It's the new story for rotational motion. And with that story, there's also a equation, a work energy relation. Here it is. If you look at this equation, over on the left-hand side here you see the torque, the net torque that's exerted on the rigid body. That transfers energy to the rigid body, does work on the rigid body. W is the work done on the rigid body. This equation relating the torque and the work looks like the equation relating on the previous slide, the force and the work. The work done by a force was force times the distance. And the work done by the torque here, so the work done by the torque is the torque times this angular distance here. And so they're equivalent equations, one in a rotational world, one in a translational world. Over on the right-hand side, well, that energy that gets transferred correspondingly changes the rotational kinetic energy of the object. And here's the change in rotational kinetic energy. And that change in rotational kinetic energy is the difference between the final kinetic energy and the initial kinetic energy. And these equations are how we recognize, how we see rotational kinetic energy in the rotating motion of a rigid body. So it's 1/2 I omega squared is the final rotational kinetic energy. 1/2 I omega naught squared is the initial rotational kinetic energy. The I's are rotational inertias. They're like the inertias, M's, the masses in translational kinetic energy. The omegas and omega naughts, so the final and initial angular velocities, they're like the V's and V naughts, the final and initial velocity, linear velocities in translational kinetic energy. So not only does this understanding of the rotational motion and energy transfer in the rotational motion mirror the understanding of energy transfer and energy in translational motion, but these equations, all of these equations are parallels of one another. If I just flip back to the previous slide, these equations here exactly parallel these equations here. They're just the same equations, one written in a rotational language, the other written in a translational language. Okay. Just to show you that most clearly, I've written the work energy relations for rotational motion and translational motion side by side on this slide. So over here on the left-hand side, we've got the work energy relation for the action of a force and translational motion. And over here on the right-hand side, we got work energy relation for the action of a torque and rotational motion. And so you see in both cases that for translational motion, forces do work, is the work done, and that corresponds to a change in kinetic energy, where the kinetic energy is 1/2 times the mass times the square of the speed. And you see equivalently in the rotational case that a torque does some work, here it is, and that corresponds to a change in rotational kinetic energy, where the rotational kinetic energy is 1/2 rotational inertia, I, times the square of the angular speed, omega squared. And so they're perfect mirrors, perfect parallels of one another in rotational and translational worlds. In both cases, for example, the work done is a scalar quantity. It has no direction, it has no orientation. It's just a number of joules that are added to or subtracted from the rotating or the translating object. So the work done can be a positive number, can be a negative number, can be zero, but it doesn't have an orientation. It doesn't have a direction, like the forces and the torques had a direction to them. So this really deepens our understanding, broadens our understanding of rotational motion. We're going to see that. And we're going to see it by looking at a couple of examples of applying energy concepts and specifically energy conservation to rotational motion involving rigid bodies. Okay, so here we're going to go back to, this is an old slide, obviously, from the last time I taught the course. But I don't know if Mythbusters is still on TV. But when my kids were young, we always used to watch Mythbusters together. And here we are in the White House, in the Oval Office. And Adam, Jamie, you roll a blueberry, a cookie, and a donut down an incline, who wins? So who wins this race? Now, we talked about this race between a sphere and a cylinder and a ring in previous class. We're going to re-examine this problem of the race between the sphere, cylinder, and ring in this class, but now we're going to do it from a energy perspective, rather than doing it from a torque and force perspective. So we're going to get a new look, a new view, an old problem. Okay, so I made a sketch of the question that we were asked. We've got an incline, here it is in blue, and we've got a object at the top of the incline, and it's going to roll down the incline. And this object, you know, might be the sphere, it might be the cylinder, or it might be the ring. Ultimately, we've got to do the calculation for the sphere, the cylinder, and the ring. But we'll just for now imagine one of those three cases. So the object is starting from rest, which means that its initial linear velocity is 0. And its initial angular velocity is 0. And then it's going to roll down the incline, and it's going to acquire some linear velocity. Here's the final linear velocity, VF, and we can think of that as the motion of the center of mass of the rolling object. And it's going to acquire some rotational velocity. Here's the final rotational velocity, omega F. And we can think of that as the angular velocity of the rigid body about the center of mass. So at the bottom of the incline, it's rotating and translating. At the top of the incline, it was at rest rotationally, at rest translationally. Well, what we're going to do is calculate that final speed at the bottom of the incline under the assumption it started from rest at the top of the incline. And we're going to do it by applying energy conservation ideas, understanding that in this problem now, there's both translational kinetic energy associated with the translational motion from the left to right, and there's rotational kinetic energy associated with the rotating motion of the rigid body about its center. Okay, so let's see how that's going to work. It'll take us a couple of slides here, but we're going to figure out we're going to figure out the final velocity of the rotating object, and that's that quantity Vf. We've denoted it Vf. Okay, so here's my starting point. This is just energy conservation. Whatever energy there was initially at the top of the incline, the total energy at the bottom of the incline, the final energy at the bottom of the incline must be the same. So the initial energy equals the final energy. I then break out the initial and final energies into the different forms of energy that are relevant to this particular problem. So here they are initially, and here they are finally. In this problem, I've got to consider, well, gravitational potential energy. The object started at a higher elevation, it ended up at a lower elevation. I've got to consider translational kinetic energy. The object started moving from left to right, and I've got to consider rotational kinetic energy. The object starts rotating about its center. So those are the three types of energy. And just to be general, I said that, you know, in principle, there could be gravitational, translational kinetic, and rotational kinetic energies to begin with. There could be gravitational, translational kinetic, rotational kinetic energies finally. I then said, well, look, I understand how these energies work. So I understand that the gravitational potential energy depends on your elevation, your height, h. I understand that the translational kinetic energy depends on your speed, v. And I understand now that the rotational kinetic energy depends on your angular speed, omega. So let me fill all those expressions or understandings of those types of energy into the energy conservation equation. Okay, so here is the initial kinetic energy at this elevation h. It's mgh. And here is the final kinetic energy at the bottom of the incline, 0. This 0 here on the left-hand side, that's the initial kinetic energy. The object wasn't moving, 0 initial velocity. So there's no kinetic energy. And then it acquires some translational kinetic energy. That's over here on the right, 1/2 mvf squared. And then likewise, this 0 here is the initial rotational kinetic energy. The object initially wasn't turning. And so there was no initial rotational kinetic energy, but at the end of the incline, bottom of the incline, it is rotating. Here's its angular frequency, angular speed, omega f. Here's its associated rotational kinetic energy. So this equation here, relates the height that the object was released from at the top of the incline to the angular speed and linear speed of the object at the bottom of the incline after rolling down the incline. We can't immediately solve this equation, though, for the final speed. We can't immediately solve it because we don't know the final angular speed, and we would have to know the moment of inertia of the object. So that there's two things I've now got to do to this equation to allow me to solve it for the final speed. Let's go ahead and do that. So the first, I'm going to go through this slide pretty quickly because we met this slide before and I keep recycling this slide. When an object rolls down an incline, for example, as I say, there's both rotational motion about the center of the object and there's translational motion of the center of mass of the object. Those two motions are related to one another. The linear coordinates, of the translational motion over here on the left, for example, the velocity of the speed of the moving object, are related to the angular coordinates that describe the rotational motion of the rigid body about its center. For example, the angular velocity of the rotating rigid body. And so in this problem of the objects rolling down the incline, where they're acquiring both linear motion and rotational motion, their linear velocity and their angular velocity, the v and the omega, are related to one another through the radius of the rolling object. And so this v equals omega r is a relation between the rotating motion and the linear motion that we can use. So we're going to use that. And then the other thing that we're going to use are the moments of inertia. So in this problem, we're considering three objects. A ring is one of the objects. Oh. A ring is one of the objects. So that on this little table here is this cylindrical shell. And here's the ring's moment of inertia. It's half mr squared. The blueberry, that's a solid sphere. That's the second of the rolling objects. Here's its moment of inertia. It's 2/5 mr squared. And the solid cylinder, that's the cookie, here's its moment of inertia. That's 1/2 mr squared. And in comparing these three moments of inertias of these three objects, and maybe it's worth thinking about, let's imagine that the cookie, the blueberry, and the donut had the same radii and the same masses. So the m's and the r's were the same. Then their rotational inertias would be in proportions of these coefficients. There's a 1 here, a 2/5 here, and a 1/2 here. So their moments of inertia would be in proportion to those numbers, and it would be in those ratios. And those ratios, or those numbers, are just reflections of the shape. What distinguishes the same mass, same radius, blueberry, cookie, and donut is their shapes, their ring shape, their solid cylinder shape, their solid sphere shape. Okay. So I'm going to now just plug in the results of those last two slides, those relationships between rotational and angular motion and the moments of inertias. So on this slide, for concreteness, I'm just doing the case of the cylinder. And so I'm going to plug in the cylinder's moment of inertia. But you would do the same thing for the sphere, and you would do the same thing for the ring. You would plug in their moments of inertias. And specifically what I want to do, let me hide, this slide's a little bit busy. Here's the equation from a couple of slides ago, which was energy conservation. It contained the height of the object at the top of the incline. It contained its linear speed and angular speed at the bottom of the incline. And I'm going to add in a couple of things. I'm going to replace omega f, the final angular speed, with vf, the final linear speed. Omega f is vf over r. So that's one thing I'm doing. Do it here. And the other thing I'm doing is replacing this moment of inertia of the cylinder. I'm going to write it in terms of its mass and its radius. I'm doing that here. And so that's the one change I've made. Now, there's a couple of interesting things happen. So we've got an r squared in the numerator and an r squared in the denominator, and these r's cancel out. So that's neat. Every term, if you look, all three terms have the mass of the rolling object in it, so the masses cancel out. And the only quantities that are left in the equation then are the acceleration of gravity, and then the parameters of the problem, the height, the elevation of the object initially, and the final speed of the object finally. And so you can rearrange that equation to get this result, that the final speed is the square root of 4/3 times the acceleration of gravity times the height of the incline. Now, if you look at that equation, there's a lot of sense that's embedded in that equation, right? The object rolls under gravity, so the G is there. We expect the G to be there. The higher the object started, then we would expect it to be rolling faster when it reaches the bottom. And indeed, that's the case. The greater H, the greater the final speed V. And then there's the 4/3. And interestingly, the 4/3 actually reflects, because we had to plug in the moment of inertia, actually reflects the shape of the object, that it was a cylinder. So the 4/3 comes about in this calculation because the rolling object was a cylinder. And when we do the sphere and the ring, we'll get a different number that isn't 4/3. So I did the other two cases. I won't go through them here, but I'm going to quote the results for you. Here are the other two cases. So here's the ring, here's the cylinder we just worked out, and here's the sphere. So in fact, all three cases are here. And the only difference in the calculations is when you do the ring, you fill in the ring's moment of inertia. Like when we did the cylinder, we filled in the cylinder's moment of inertia. When we did the sphere, we filled in the sphere's moment of inertia. Because of the different geometrical factors in the equations for the moments of inertia, the 1, 1/2, and 2/5, we get different geometrical factors in these equations for the speed. So in all cases, the speed depends on gravity, acceleration of gravity. Of course, that's got to be because gravity pulls the ring, the sphere, the cylinder down. In all cases, the speed depends in the same way on the height, the elevation of the incline. How far are you going to roll the object down the incline? But these numerical factors are different because of the different shapes of the sphere and the cylinder and the ring. You see, the largest number corresponds to the sphere. So the sphere is going fastest at the bottom of the incline. The smallest number, it's a 1, corresponds to the ring. That's going slowest at the bottom of the incline. The implication, right, is the sphere got there first by going the fastest. The ring got there last by going the slowest, which is exactly what we figured when we thought about this problem from the old sort of force-torque perspective. So we validated the old force-torque perspective on the sphere ring winning the race, but we've solved the problem in a new way. It's actually a quicker way, I think, using this energy perspective, that the original kinetic energy at the original gravitational potential energy at the top of the incline has been morphed into, changed into a combination of rotational and translational kinetic energy. And the point is that the sphere, the ring, the cylinder share differently rotational and translational kinetic energy. And that's why the linear speeds are different for the sphere, the cylinder, and the ring. And that sharing of the rotational and translational kinetic energy is governed by the moments of inertia, is governed by their rotational inertias. Let me just show you this one equation right down at the bottom. Early on in the course, we solved the problem of an object sliding down a frictionless incline. And we found the speed for the object at the bottom of the frictionless incline when it slid. And it was this expression here. So I just looked it up from an early lecture. And this sliding down the incline has a factor of 2 here. So if you raced a sliding object with the rolling sphere, cylinder, and ring, the sliding object on a frictionless incline would win the race. There's a factor of 2 there. The sphere comes next with the factor of 10/7. The cylinder third with a factor of 4/3, and the ring last with just a factor of 1. Okay. Let's look at a second problem that we've also solved in the past, but we can now solve by energy conservation methods. And it's the one from, this is from last class. This is like, we just went back to Tuesday and we're doing the same class again, but I'm doing it a different way. I'm doing it with energy concepts. So in this problem, we've got a bucket that's attached by a rope to a pulley, and we're going to release the bucket and it's going to go down the well. And in this version of the problem, we're asked to use energy conservation, use concepts of energy to find the speed of the bucket after it's dropped 5 meters down the well, after falling 5 meters down the well. And we're given some masses and dimensions of the bucket and the pulley. We've got a 5 kilogram pulley, we've got a 3 kilogram bucket, for example. Okay, so before I go ahead and solve this problem with energy conservation, I wanted to recycle this slide just one more time. I've only shown it 5 times so far. I want to recycle this slide and remind you that the bucket's translational motion and this pulley's rotational motion, they are 2 different objects, but they're tied together by a rope. Their rotational and translational motion are related, connected to one another. And on this slide, assuming the rope doesn't slip, assuming the rope doesn't slide on the pulley, the coordinates describing the bucket's motion, so those are these linear coordinates over here on the left, are related to the coordinates describing the pulley's rotational motion, these rotational coordinates here on the right, through these equations. So for example, the linear velocity v of the bucket is related to the angular velocity omega of the pulley by this equation here, v equals omega r, where r is the radius of the pulley. Okay, so we're going to use that. And we're going to use that, what I call a no-slip condition. It means that the rope is not slipping or sliding over the pulley. And we're going to use that when we apply energy conservation to the problem. And so on this slide, I'm actually solving the entire problem. So I started with a picture. This picture on the left-hand side, this is the before. Why do I keep doing this? I don't know. This picture on the left is before the bucket falls. And this picture on the right, this is after the bucket has fallen, the 5 meters. And here is that distance fallen. This is 5 meters in the problem. And I've added to the pulley in green with radius r and the bucket in this nice magenta. I've added to those pictures some of the quantities that I know. So I know the radius of the pulley is 0.6 meters. I know the mass of the pulley is, I called it uppercase M, 5 kilograms. I know it's a solid cylinder, and its moment of inertia is then 1/2 mr squared. And I also know the mass of the bucket. It was 3 kilograms. So I know all those quantities. Initially, the bucket and the pulley are both at rest. The bucket is not undergoing translational motion. Its initial velocity is 0. The pulley is not undergoing angular motion. Its initial angular velocity is 0. So VI, omega I are both 0. Finally, well, the bucket is undergoing translational motion, and the pulley is undergoing rotational motion, and I've called their velocities, I call VF is the final linear velocity of the bucket, and omega F is the final angular velocity of the pulley. Okay, so that's a picture of what's going on. We're going to apply energy conservation. That whatever initial energy this system had is going to be equal to the final energy of this system. We're not going to create any energy or destroy any energy. We've got no powers to do that. Nobody has any powers to do that. We're going to conserve energy. And so this system is going to conserve energy. This system of the bucket and the pulley is going to conserve energy. Now, in this problem, right, the initial energy is in the form of gravitational potential energy, and that energy gets converted to forms of translational kinetic energy of the bucket and rotational kinetic energy of the pulley. So that's what's going to happen. So in the second line of my solution here on the left and right, I expand that initial energy into the possible forms of energy in this particular problem, where there's gravitational potential energy, there's translational kinetic energy, and there's rotational kinetic energy. So that's initially, all the subscripts I's on the left, and that's also finally gravitational, translational kinetic, rotational kinetic energies on the right-hand side. And then I say, well, look, just like in the last problem, I understand how gravitational potential energy works. I understand how to see translational kinetic energy in the motion of an object. I understand how to see rotational kinetic energy in the motion of an object. Let me fill in all that understanding. So the initial height of the bucket is h. Here's its initial gravitational potential energy, mgh. The final height of the bucket is 0. Here's its final gravitational potential energy, 0. The initial kinetic, translational kinetic energy of the bucket is 0 because it's at rest. The final translational kinetic energy of the bucket is 1/2 mvf squared. And then likewise, the initial rotational kinetic energy of the pulley is 0. The final rotational kinetic energy of the pulley is 1/2 I omega f squared. So that's kinetic, that's energy conservation, and me filling in all the forms of energy that are relevant, present in this particular bucket and pulley problem. Okay, so that was a big step. The only problem with this step is that we still can't find the final speed of the bucket because we got some other things that we haven't yet expressed or haven't yet worked out, and they're the angular velocity of the pulley, and they're the moment of inertia of the pulley. So my last step in this problem is really to say, well, look, I can write the moment of inertia of the pulley in terms of the mass and the radius of the pulley. I can write the angular velocity of the pulley in terms of the linear velocity of the bucket, and I can feed those two things in. And so over here on the right, that's where I replaced omega f with Vf. Over here next to it, that's where I'm replacing I with the mass and the radius of the pulley. The nice thing about doing that is that the radius in the numerator here of the moment of inertia and the radius in omega f squared here in the denominator of the expression for omega f, they cancel each other out. So the r's cancel out, and you have an equation that contains the height, the elevation, that was 5 meters, we know that, contains the masses of the two objects, the pulley and the bucket, we know them, 3 and 5 kilograms. And so we can rearrange it and solve for this final velocity. And so here I've just rearranged the equation. Again, there's a lot of things that make sense about that equation. The final velocity depends on there being gravity. the bucket falls because of gravity. So it's not surprising to see the acceleration of gravity here. The speed of the bucket depends on the height that it fell. The further it fell, the greater the speed. That makes sense. And then there's this factor. This is just a number ultimately. It's a ratio of masses. This factor that multiplies the GH in the square root. And it's really a comparison of the masses of the bucket and the pulley, which is going to determine, you know, kind of what fraction of gravity is able to just pull the bucket rather than having to rotate the pulley. And so at this point, you can plug in all the numbers. So I plugged in the various numbers, the 3 and the 5 kilograms for the mass of the bucket and the pulley, and I found the speed. The speed after falling. The speed after falling this 5 meters. And this speed is less, I haven't calculated it here, but this speed would be less than if I just dropped the bucket. If I dropped the bucket, the speed would be greater after falling 5 meters. If I release the bucket on the pulley, the speed is smaller than just dropping the bucket. Okay, well that was fun. So that's rotational kinetic energy. And now I want to turn to, in the last half an hour, I want to turn to angular momentum. And I want to introduce angular momentum by recalling linear momentum. And then we're going to look at an angular momentum problem or two. Okay, so let's just remind, I've got one slide here to remind us. It's like we can sit back in our chairs, drink our coffee. Yeah, I need mine. And relax while we just, you know, recall what we learned about linear momentum. And then we're going to introduce a new thing, angular momentum, in parallel, mirroring linear momentum. So I sometimes like to think of linear momentum as sort of a power of motion. I think of it that way because, you know, a big, fast-moving truck would have lots of linear momentum. A slow-moving fly would have not much linear momentum. The equation for linear momentum of a moving object is simply its mass, or inertia, times its velocity, its linear velocity. So this is the basic equation of linear momentum here. And one way of picturing forces is that they transfer linear momentum. So when a force acts on an object, in general, it changes its linear momentum. We call that change in linear momentum, we call it the impulse. And the impulse that's given by a force, so delta P, the change in momentum, the impulse given by a force, is related to the force by, this equation here. So those are two key equations for the definition of linear momentum in terms of the motion of an object and the relation of forces and how forces can change linear momentum. The other important point about linear momentum is that if you have a system where there's no forces, external forces acting, if you have a system where there's no external forces acting, and that would be if we consider this falling apple and the earth to be a system. If I thought about the apple on its own, that's not that has external forces acting on it. If I think about the earth on its own, that has external forces acting on it. But the apple and the earth here in this picture are a system where no external forces are acting on it. That type of system conserves linear momentum, and that's the value, that's the usefulness in problem solving of linear momentum. Okay, so that was remembering linear momentum. Let me clear that and introduce angular momentum. Okay, so like linear momentum was kind of the power of motion, angular momentum is kind of the power of rotation. So if imagine you've got a giant tractor wheel that's rotating very rapidly. Well, that contains a huge amount of angular momentum. But if you had a little wheel on a 3-year-old's tricycle that is rotating very slowly, that just contains a small amount of angular momentum. So in that sense, angular momentum is kind of the power of rotation. The fast rotating tractor wheel has a lot more power of rotation. The slow rotating tricycle wheel has a lot less power of rotation. We can define angular momentum. We give it the symbol L here in terms of the angular velocity of a rotating object and its rotational inertia, rather than defining linear momentum in terms of the linear velocity and its inertia or mass. And so the equivalent equation is this equation here. So if you have a rotating object, its angular momentum L is equal to its angular velocity omega times its rotational inertia I. And these three quantities parallel the three quantities in P equals mv. So linear and angular momentum, the L and the P, the angular velocity and linear velocity, the omega and the V, and then the inertias, the rotational inertia and the mass for inertia, the I and the M. So they just parallel one another. Like we could view forces as transferring linear momentum, we can view torques as transferring angular momentum. So that's one way of picturing forces, is that they're agents of transfer of angular momentum. We call that an impulse too. And the change in angular momentum, we call that delta L. And the change in angular momentum that's achieved by a torque acting is given by this little expression here. The change in angular momentum when the torque acts is the torque times the time interval that it acts for. And that exactly parallels the equation for linear momentum change. The change in linear momentum was equal to the product of the force that was acting times the time interval that the force acts. So they really are parallel equations. The power of linear momentum is angular momentum is same idea as the power of linear momentum. It's momentum conservation. So just like in the linear momentum case, if you have a system on which there's no external forces, then that system will conserve linear momentum. If you have a system involving no external torques, then that system will conserve angular momentum. And so here's an ice skater. If you're worried what this is an ice skater spinning in the ice rink on the Earth. And individually, the ice skater and the Earth might not conserve momentum, but as a system as a whole, when the ice skater starts rotating or stops himself rotating with his skates, the entire system of the Earth and the ice skater, they do conserve angular momentum. And so that's the power of angular momentum arguments, just like it was the power of linear momentum arguments. So here's just a summary of that, because I just wanted to show you very directly the parallels between linear momentum and angular momentum. So linear momentum's over here on the left-hand side in this overhead. Angular momentum's over here on the right-hand side in this overhead. Their definitions in terms of either the linear speed or the angular speed are equivalent definitions. It's just those speeds times either the mass or inertia or the rotational equivalent, the moment of inertia or rotational inertia. And then what forces do and what torques do is equivalent. the relationship between torques and change in momentum is the same as the relationship between forces and change in linear momentum is the same as the relationship between torques and change in angular momentum. And so these equations are the same equations in the world of translational motion as these equations are in the world of rotational motion. Okay, so I want to look at, in the last 20 minutes, some examples of angular momentum conservation. And I want to start by showing a couple of demonstrations. Let's do this. So I'm going to share a different screen. Yes, I was thinking what I'm going to do. Okay, so we're going to watch a ice skater spin. So the ice skater has to get herself spinning in this little video, and she does that by exerting torques on the ice or the earth, and those change her angular momentum. So first of all, you're going to see the ice skater acquire some angular momentum. And she acquires it, as I say, by exerting torques, digging the blades of her ice skates into the ice to exert forces to create torques that generate her rotational motion. Then you're going to see a beautiful example of angular momentum conservation. So the ice skater will be spinning, rotating with her hands outstretched. Then she's going to bring her hands inwards. When her hands are outstretched, the ice skater has a larger moment of inertia, rotational inertia, because her mass on average is further away from her axis of rotation. When her hands are brought inwards, then she has a smaller moment of inertia because her mass on average is closer to our axis of rotation. But during that change in her rotational inertia, her moment of inertia, her angular momentum is conserved, is not changed. And we're going to see what happens because of angular momentum conservation in this video. So I'll play it one more time, but watch as she pulls in her arms and just watch, because she's significantly or substantially decreasing her moment of inertia, because she's centering her mass much more on her axis of rotation. If her moment of inertia decreases and her angular momentum's conserved, she has to rotate much faster. And that's how she was rotating, I think it said 300 revolutions per minute. I mean, that's an amazing rotation. And she got this world record for fastest rotation. Didn't know there was one, but she got it. Let's play it one more time. Okay. And so if you're, a champion ice skater, then, and you're doing these spins and turns and whatevers, angular momentum, understanding angular momentum, understanding moment of inertia, your moment of inertia are very important. Okay, there was a second video I was going to show. So I thought, I saw that video, and I thought, I want to try something like that. I'm going to try, changing my moment of inertia as I spin, and how far, maybe I could get the world record. I could go faster than 300 revolutions per minute. And so I'm going to try that now. And so I actually, the first problem I realized was that I can't ice skate. So I can't do it on ice, but I built this arrangement with a chair mounted on a rotating wheel. And so I'm going to not do this on ice, but I'm going to rotate myself on this rotating chair. And I thought, well, here's something the ice skater didn't think of. She just pulled her arms in to make herself rotate faster. But what if I hold two big old masses in my outstretched arms and then pull that in? That's going to change. I know it sounds like cheating, but it's going to change my moment of inertia even more than if I just pulled my arms in. And so maybe this way I can get the world record. Okay, so now I'm going to start pulling my arms in and pushing them out, and watch my speed change. As I pull my arms in, I go faster, and I push my arms out, I go slower. And that's because angular momentum is conserved. If I reduce my moment of inertia, I have to correspondingly increase my angular velocity to maintain the angular momentum. Okay, well, as you can tell, I didn't get to 300 revolutions per minute, but I cut off the video there because even after that, I was extremely dizzy and felt extremely unwell. But anyway, it was I thought a good attempt. Let me go back to the slides. And I got a quiz. Okay, so I think we're coming up to the end of the quiz. So when the spinning skater pulls in her outstretched arms, okay, or when I pulled in my outstretched arms, my or her angular velocity increased. Okay, so she span faster, I span faster. But our angular momentum, which depends both on angular velocity and moment of inertia, that remains unchanged. So the correct answer is that her angular velocity increases, but her angular momentum is unchanged. So this guy here. Okay, so let's move on. And let's look at a numerical problem of angular momentum conservation. Okay, so in this problem, we're told that a merry-go-round rotates at 0.15 revolutions a second with a 85 kilogram man standing at a point 2 meters from the axis of rotation. We're then asked, what is the final angular velocity or final angular speed when the man walks from that point that's 2 meters from the axis of rotation to a point that's 0.7 meters from the axis of rotation, so closer to the axis of the rotation. I mean, I have no idea what this man is doing on this merry-go-round, but anyway, he's going to walk from 2 meters from the center to 0.7 meters from the center, and we're going to figure out how the speed of the merry-go-round changes. We know it initially, we want to find out the final speed. In that sense, it's almost similar to the problem of the ice skater, increasing her speed or changing her speed, or me on the chair increasing or changing my speed. As we do this calculation, we're going to, as indicated here, assume that the merry-go-round is just a solid cylinder to keep things simple with the man on it. The merry-go-round is a solid cylinder with a radius of 2 meters. Okay, so the first thing I did is not to apply immediately apply angular momentum conservation to find the final speed of the merry-go-round. We are going to do that, but the first thing I've got to do is a little sort of initial work to find out the moment of inertia of the merry-go-round, initially with the man far from the axis of rotation, and finally with the man closer to the axis of rotation. So I try to draw those two situations here. This is before the man steps closer. This is after the man steps closer. So this beautiful orange color is the merry-go-round. This is a helicopter view, right? We're hovering over the merry-go-round with the man walking on it. And the orange color is the merry-go-round, and the man here is in this nice green color. And so you see the merry-go-round's radius is 2 meters. I called that little r. And the man's distance from the axis of rotation, I called that uppercase R, and I gave it a subscript I for initially. That was initially 2 meters. But then after the man steps towards the center of the merry-go-round, then that distance is 0.7 meters. I called that R, uppercase R, subscript F. So we know, we were told the man's mass, we were told the merry-go-round's mass. So actually we can calculate, this important point from an earlier class, we can calculate the moment of inertia of the entire system. How do I do that? So the first step is that the moment of inertia of the entire system of the man and the merry-go-round is the sum, simply the sum of the moment of inertias of the man moving in a circular path and the merry-go-round rotating in a circular path. So we've just got to add together those two contributions. The man's moment of inertia is like a point mass going in a circle. It's mr squared. The merry-go's moment of inertia, it's a cylinder. Its moment of inertia is a half mr squared. So these are the moment of inertias of the man and the cylinder, two contributions. Now the moment of inertia of the merry-go-round, the cylinder, doesn't change. It's just 1/2 times little m, the mass of the merry-go-round, times the square of little r, the radius of the merry-go-round. What changes the moment of inertia is the man moving closer to the axis of rotation. So his final position is 2 meters, is further from the axis of rotation. His initial position is 2 meters. It's further from the axis of rotation. The final position is 0.7 meters. It's closer to the axis of rotation. That changes the moment of inertia of the entire arrangement, just like pulling my arms in, or was it Natalie, the ice skater, pulling her arms in changed her moment of inertia. Okay, so I did the calculation for the initial moment of inertia, the final moment of inertia. Actually, they're quite different. 390 kilogram meter squared initially, 92 kilogram meter squared finally. They're quite different because most of the mass is the man, okay, and the man has changed its position quite a lot. And the moment of inertia goes as the square of that, the location of his mass. And so there's a big change of moment of inertia when the man walks inwards. And that's actually true when Natalie pulled her arms in. There was actually a big change in the moment of inertia. And when I put my arms in with the weights in them, there was a big change in the moment of inertia. And in all of these cases, there's therefore a big change. It's going to be a big change in the speed, big corresponding change, equivalent change in the speed. Okay, so now we've got the moments of inertias. And we can go on and apply angular momentum conservation to find the final angular velocity of the system, knowing the initial angular velocity of the system. And so here are the sketches from the last slide, but I want to point out now that the initial angular velocity, I converted it to radians per second. It's 0.94 radians per second. I called it omega I, and we want to find out this final angular velocity. I've called that omega F. We have to determine that. But now we're in a position where we know these two moments of inertia. Okay, so I'm going to apply angular momentum conservation. The initial angular momentum, I called it Li, is equal to the final angular momentum. I call that LF. Just like for the skater pulling her arms in, for me pulling my arms in, the angular momentum was conserved during those acts of pulling the arms in or this man walking inwards. I then write the initial angular momentum in terms of the initial angular velocity. Write the final angular momentum in terms of the final angular velocity, using the definition of angular momentum in terms of angular velocity and rotational inertia that parallels the definition of linear momentum in terms of linear velocity and mass or inertia. Well, I've built myself here an equation that relates the unknown final angular speed to the known initial speed and the known moments of inertia. So I can go ahead and rearrange this equation for the final angular speed in terms of the initial angular speed and the ratio, the fraction by which the moments of inertia have changed. And we see that as the moment of inertia goes down, and it went down by roughly a factor of 4, the speed went up by roughly a factor of 4. So the man is rotating and the merry-go-round are now rotating about 4 times faster because the moment of inertia is now about 4 times smaller. And that's how Natalie got the world record, and that's how I failed to get the world record. Anyway, that's a tour through rotational energy concepts and angular momentum concepts that give us a new perspective, a new viewpoint for thinking about rotational rigid body problems. They give us both a new understanding, a greater depth of understanding of rotational motion of rigid bodies, but also just new techniques, new approaches to answering problems. And it really parallels the work we did in translational motion, where we had force perspectives and energy perspectives. Now in rotational motion, we got torque perspectives and energy perspectives. I'm going to finish there. And in next class, we've got a 1-lecture class on a related topic. We've been talking about rigid bodies. I'm now going to imagine that those bodies can deformable bodies.